This conference will now be recorded.
Okay, so we had started induction and we had already learned few things like the experiments Joseph Henry and Michael Faraday they had performed uh, to actually know about the induction, and what we have learned so far from their experiments is that change in the flask linked in a coil, okay, change in the flask actually produces a magnetic produces a uh, EMF, an EMF, and that EMF in turn produces a current. Okay, so the question was that whether like we have seen that varying current can create magnetic field, and in this chapter we are seeing that varying magnetic flux or varying magnetic field can in turn produce an electric current. So that is what we are learning. We have already learned up to motional EMF, Lenz's law. So Faraday's law of induction we have learned, and then in the last class we had learned Lenz's law and energy conservation, and also we had learned motional electromotive force. So today what we will be learning is uh, the inductance. So today we will be learning inductance. Let us see what is inductance and then things like that. We'll see over here. Okay. So we have seen in the beginning of this chapter that there are two coils. There are two coils, and change in, see, if current is flowing here in this coil C2, so it will produce a magnetic field, and if the current is time varying or current is changing in this coil, then flask will, see, the magnetic field created by this coil will be linked as flask in this coil C1, and if the flask changes due to either due to motion of this coil C2 or relative motion between them, or due to the change in the current, the flask linked with this coil C1 changes, and we have seen that in turn there will be a current flowing in this. Okay, that means if you have two coils, change in current in one coil will actually produce a magnetic an electric current in the other coil. If I say more correctly, I'll say that the change in the flask in one coil in C2, suppose, produces a current or EMF, an EMF in C1. So that means they have some coupling between them. Okay, some coupling between them, or some influence of C2 on C1. See, not only this, even if you have only a single coil, just C1, and if you flow a current, varying current, AC current, okay, current which is time varying, you will see the change in the flask in C1 will produce an EMF in itself. Okay, so there are two things I have discussed now. So if I have two coils, if you pass a current in one coil, if it is time varying current, or maybe somehow if you change in the flux in C2 coil, then it will induce an EMF in the C1 coil. Okay, so this is actually called mutual inductance. This is called mutual inductance, or in other way also it is true. Suppose I pass a current in C1, it will induce an EMF in C2. So it can be this way or this way. Okay, so this is called mutual inductance. And if I have a single coil C1, if I pass a time varying current or AC current in this same coil, it itself will produce an EMF which is called back EMF in itself due to the change in the current in itself. So this is because it is happening due to its own, due to the change in the flask in its own. That's why this is called self inductance, this one. So if you have two coils, change in the flask in one coil will produce induced EMF. So this is called inductance. Okay, we learned that mathematically what it is. And if the induction is happening in a coil due to other coil, this is called mutual inductance or in mutual induction. The phenomena is called mutual induction, and the coupling constant between them, because they have some coupling, because of that only one coil is producing an induced EMF in the other. So that coupling constant is called mutual inductance, coupling constant, and the phenomena is called mutual induction. So coupling constant is called mutual inductance. Okay, and when the same coil is producing induced EMF in itself due to the change in the flask in it, that means that phenomena is happening for itself. So it is called self inductance. This is also the actually the coupling constant is called self inductance, and the phenomena is called self induction. Okay, so this is what our aim today to learn. Let us see first what is mutual inductance. As I said, this is a coupling constant between two coils. Tell you that so what I told that if this is C2, this is C1, the change in the flask in this will produce an induced EMF in this. Okay, that doesn't mean that if there is a flask 2 here, okay, the same flask is linked over here. It is not true. What I mean to say is, suppose this is coil C1 and this is coil C2. The area, you can see the area of the coils are not same. So what we have learned, flask means the magnetic field into area. Okay, if you write in proper notation BA cos of theta. Okay, BA cos of theta, if I take that theta is 0, then that is the maximum flask. I am just considering that the maximum flask is linked. Flask linked means if I have a source of magnetic field over here, so when the magnetic field lines are passing across this area of the loop or the coil, then we say, see, if I say there are 3 to 5 magnetic field lines are passing through this, so I'll say that 5 uh, like amount of 5, or in terms of we can write in terms of that the C1 is linked with, like flask linked with the C1 is a 5 something like that. Okay, this is called linked. That means if the field lines are passing through any coil, then we'll say that flask is linked in that. That means if suppose the current a current time varying current is current is flowing in this coil 1, okay, it will create a magnetic field. Okay, first of all, since the current is flowing, we know on the axial point there will be a magnetic field. Okay, and see this coil C1 is placed on the axial, like perpendicular to the axial like axis of this C2 coil, obviously. So if it is creating a magnetic field, so like this, so the field lines will pass through this. So this is called magnetic like this is called flask linked. Okay, flask linked. See, it may create many magnetic field lines, so all may not go through this C1 coil. So when I am saying that the change in the flask in C2 will produce a magnetic field, that means change in the flask here, this is C2, this will produce a change in the flask in this one, which is linked in this C1 coil. Okay, since the area is different here, so the flask linked in this also will be different. But here you look, the flask linked in any, see, any coil of these two, either of these two, will be actually proportional to the current in the other coil. So so flask linked in this case, suppose flask linked in C1 coil is phi 1, this will be proportional to the current flowing in, if I just say this is I2 flowing in the coil C2. So this is actually a relationship between the flask linked in the coil C2 due to the current in the, sorry, flask linked in C1 due to the current in C2 coil. Okay, so this is how we'll write the flask. If suppose I have a coil of n turns, then the amount of flask linked in this is n phi 1, then proportional to, this is proportional to I2. So if I apply Faraday's law of induction, so I can find out the induced EMF, magnitude of induced EMF is equal to minus d phi 1 dt. This is what we know. So here it will be n phi 1 because if there are n turns. So I can write, see again, this n phi is directly proportional to I2. So I can write this as I2. Okay, this I can write. I hope I should not write this, I should write proportional here. Okay, now we'll see that uh, we'll we'll see for two solenoids. Okay, so instead of taking circular coil, we'll calculate mutual inductance for two solenoids. Okay, coaxial solenoid. Here you can see. Okay, I'll just show you in my presentation. Just a minute. So I'm just going to uh, see how mathematically we can calculate the mutual inductance. So mutual inductance I have not told you. Okay, let me tell you what is mutual inductance. So we have seen that induced EMF can be calculated as this n phi 1 dt. Okay, this is proportional of sorry, this is this I can write as equal, no problem, equality sign. But when I'll be writing this, see, this n phi is directly proportional to I2, so I can write this as minus d I2 by dt. Okay, this I can write. Now if I want to uh, remove this proportionality constant, so from here itself I can remove the proportionality constant. So n phi 1, so see, proportionality, if I just remove, then there must be a proportionality constant. This is actually denoted as m12 then I2. So this proportionality constant, this is called mutual inductance. For two coils, like induction produced in one coil due to the other. So this is the coupling constant, and this is called mutual inductance. And for a single coil, for itself, this proportionality constant, so n phi will be proportional to the current in itself. So we can write n phi 1 is equal to L I1. So this L is denoted for, so L is written, this is another proportionality constant for self inductance, and this is called actually induction. So this is called self inductance. We'll just come to that. Okay, so let us see mutual inductance. So we have seen that n phi 1 is equal to m12 I2. That means what? The flux produced or linked in coil 1 when current is flowing in the coil 2 I2. Okay, this is the meaning of this. So I am taking two coils, actually two solenoids as two coils. Solenoid 1, which you can see, this is actually copied from your book, NCERT textbook. So S1 is the inner solenoid, S1 inner solenoid. Okay, inner solenoid. Okay, and S2 is actually outer solenoid, outer solenoid. So see this, suppose inner solenoid has uh, has n1 number of turns. Okay, both are, suppose both are of same length L1, sorry, L. As you can see from here, both the solenoids are of same length L, and S1 has n1 number of turns. It has radius of each loop is r1, and length, anyway you know this, L. S2, the corresponding parameters are N2, R2, and L. So S2 is the outer solenoid. Now what I'm going to do is, we are just doing, we are just seeing the mutual induction. Mutual induction means I am just flowing a current I2 in solenoid S2. Okay, the outer solenoid. You can see this. This is the outer solenoid. When I pass a current in a solenoid, we know what is the magnetic field produced in that. Suppose a B2, this we know. While inside the solenoid, it will be mu 0. This will be actually for a long solenoid. That means, you know, your L is much greater than R. That means length of the solenoid is much greater than the radius of the solenoid. So at that condition, the magnetic field produced in a solenoid while inside will be axial. That means it will be, magnetic field will be along the axis direction, either this way or maybe this way, depending on the current direction. But the magnitude will be actually mu 0 in mu 0 in 2 and I2. What is this N2, small N2? This will be actually N2 by L. This is called small N2. Similarly here I can write small N1 as capital N1 by L. Okay, number of turns per unit length. So this I hope you know this because we have already learned in the fourth chapter magnetic field produced by a solenoid. So look, I have to find out the flux linked in the S1. That means in each loop, if I say in each loop the flux linked in the coil S1, flux linked in S1, linked in S1. So flux linked in S1 will be, say I have n number of turns n1 and suppose phi 1. Okay, we know this is actually directly proportional to the current. Okay, so first of all let us see what it is. This is, see, phi means, so n1 we know, phi means magnetic field. So this is actually b2 because magnetic field, see this s1 coil is oil immersed inside the magnetic field b2 into the area will be the area of the small, this one small uh, solenoid, area of each loop of the small solenoid, so pi r1 square. So this is the flux linked in the S1 solenoid. Okay, this is the total flux linked in the S1 solenoid or inner solenoid. Okay, all right. So if this is the case, now we know according to our formula, yeah. So we know that I'll just remove this part. I hope you remember this, some of this. We know that this n1 phi will be this one proportional to, so I can write this, see, n1. So this is the thing we know already. So n1 phi 1, this I am writing what is equal to that. So this is n1 pi r1 square into b2. B2, that is the field produced by the outer solenoid. What is that? This is mu 0 n small n2, then this is I2. Okay, I2. So pi r1 square mu 0 ni. So if I um, okay, so you can see this will be again equal to m1 to I2. Okay, so we can do one thing. We can write small n1, then L you have to multiply. So in this side, if I just write, look, I can just write this as m12. If I just compare the both sides, m12 will be mu 0 capital N1, then small n2 pi into r1 square. Okay, so this capital N2, if you, N1, if you want to write small n1 you can write, but in that case you have to multiply 1l because I have to divide with 1l, then you have to multiply 1l. So this is pi r1 square. So this is the value of mutual inductance in this case. And see, I have written M12. What does this mean? This is meaning that this is the mutual induction happening here. Mutual induction is happening, and the coupling. This is a coupling constant, and this constant is actually, this is called mutual inductance. Mutual inductance. inductance, and this is called mutual inductance of the coil SO1 or solenoid SO1. That is the indices here. Mutual inductance of the S1 due to S2. S2 means due to S2 solenoid. So that's why it is M12. Just like your Coulomb forces, you have written F12 or F21. Okay. So these are the things. So what we have got, mutual inductance of coil 1 due to the coil 2, or solenoid 1 due to solenoid 2, is mu 0 N1 into N2 into L pi R1 square. Okay. So this is the value of this mutual inductance for the coil 1, and I have just skipped one point, that this inductance actually depends on geometry, so ek number number 1, this is geometry of the coil. So then in it actually will be like what is the area or shape or size or number of turns. These parameters will come, and another parameter is actually relative permeability. Relative permeability, how much number of field lines can be permitted in that material. Okay, relative permeability. So these are the factors on which the inductance, whether it is mutual or self inductance, it depends on this parameter. So you can look here, see number of turns 1, n1, n2, then length. These are all actually the parameters related to geometry, shape, size, and n1, n2. These are actually the number of coils, number of turns per unit length, and this is actually, see, this is the area, pi r1 square. This, see, you can see this mutual inductance or inductance depends solely on geometry. All right. So we have got mutual inductance for solenoid 1 due to solenoid 2. But what is the value of mutual uh, inductance of the solenoid 2 due to 1? So this we can calculate in the reverse way. What we'll do in the first case, what we have done is, just a minute. So we have seen M12 and we have calculated the value. So for this case, what we have done, we had passed the current in the S2, and that S2 was producing a magnetic field, and that magnetic field, due to that magnetic field, a flux was linked in S1 coil, and that's how we have got this mutual inductance. Now we'll do the reverse way. So we'll pass a current through S1, and we'll be calculating flux linked in S2. So this is what we are going to see now. So if I write, this is N2 phi 2. So this must be N2 into phi 2 means, see, I have passed, sorry, this is I1. I have passed the current I1 through the uh, through the solenoid S1. So it will create a magnetic field B1, which is mu 0 N1 into I1. Okay, all right. So this is the flask. Sorry, this is the magnetic field which is produced in the area. See through this actually in this region, only this region. Magnetic field outside. See outside the solenoid is 0. That's why you have to be very much careful while calculating phi 2. So phi 2 you cannot write B1 into pi R2 square. You cannot write that because see this is not the area which is exposed to the magnetic field. The area of the S2 solenoid is this much. This much. That means the area equivalent to the solenoid 1 which is exposed or linked with the magnetic field created by the S1 solenoid. That means flux linked in S2 is only up to this much area, pi R1 square. So the area is same in this case as previous one. So B1 is mu 0 N1 I1 into pi R1 square. Okay, and I can write this as then. So this is the flask. So phi 2. So I can write into then mu 0 N1 I1 pi R1 square. Okay, I'll just clean it and write so that you can see it properly. So we are finding out the flux linked in S2. As I explained, the flux will be linked in the area of S2 equivalent to the area of S1 itself. So I can write N2 phi 2 is equal to N2 into B1. B1 is mu 0 N1 into I into the area exposed to that magnetic field is pi R1 square. This dimension itself, this area itself. Now I can do one thing. I can write mu 0 N1 N2 and N2 means I have to multiply L obviously here. So pi R1 square into L into this one is I1. This one is I1 because current I have passed through the solenoid 1. And we know this will be, see, N2 phi 2 according to our uh, definition of inductance, it will be M21 into current in the solenoid 1. So if I just compare both sides, okay, so this one with this one N2 phi 2, we can look. So just you just leave this I1. So M21 will be this one mu 0 N1 N2 pi R1 square into L. This is M1 M21. That means the mutual inductance of the coil 2 or solenoid, outer solenoid, due to the inner solenoid. And surprisingly, if I show you that the mutual inductance or the coupling constant between these two are actually the same. See here also mu 0 N1 N2 L I have written first, so I'll just write here pi R1 square into L. Okay, here also mu 0 N1 N2 pi R1 square into L. That means what we are getting here, M12 is equal to M21. That means the mutual inductance for these two coils are equal. So if these are solenoids, it can be generalized actually. If you have two coils C1 and C2, okay, C2 in this case also M12 will be equal to M21. Okay, mutual inductance will be same for a pair of coils. Okay, a pair of coils. So what we have learned here, that mutual inductance M12 equal to M21, and in this case we have seen it is actually mu 0 N1 N2 pi R1 square into L. Okay, so all these are actually related to geometry. All the parameters is depends on is actually related to its geometry. So now I have got mutual inductance, right? So if I have a situation, practical situation, that I have two coaxial solenoids like this, then uh, there is a current passing through the inner coil. Okay, inner coil, suppose I1, inner solenoid S1, this is S2. So you have to find out what is the induced EMF in the outer solenoid. Then you can write directly, this is suppose N2 phi 2 dt. This is again, you know, this is proportional to this, equal to the ddt of M12 or M21 I2, sorry I1, M21, sorry, M21 I1. Okay, so M21 is a constant, so it will come out of your integration derivative, and it will be di1 into dt. Okay, so if you know the current in the S1 coil, you can directly, and you have these parameters given, you can find out this, what is this. So you can directly just doing derivative of the time varying current. Okay, time varying current in the coil, sorry, solenoid S1, you can directly calculate the induced EMF in the outer solenoid, or vice versa. Okay, because M12 and M21 is same, the flux, the induced EMF actually just depends on the current in each coil. If the current in both cases are same, then induced EMF will be same in either coil. Okay, so suppose the same amount of current you like I passed in the inner coil, the amount of induced EMF you get, if the same current is passing in the outer coil, the same induction, mutual induction will be happening in the inner coil. Okay, so you can just uh, have a look in your book. So these are the things. Okay, you can just read it. So we have demonstrated the equality for long uh, coaxial solenoid, but there is a practical situation. Suppose you have been given a situation, you have been given a situation like your uh, inner solenoid is this much. That means both the solenoids are not of same length. Okay, they are of not same length. Then how do you calculate the induced EMF? Because see, we don't know how much flux linked in the outer coil due to the current in the inner coil. Okay, so in that situation, this will come into picture. This M12 is equal to M21, whether their size is same or not, that doesn't matter here. Okay, M12 is equal to M21. So if you can get this mutual inductance value, then directly from here, even though their size is not same, still you can find out the induced EMF in the outer coil due to the inner. Okay, or vice versa. So here in this case we have taken, for simplicity, we have taken the L. See, L1 and L2 are same actually in this case. But in this case, this is L1 and this is L2, where L2 is greater than L1. Okay, that's how we have got. Like then we, in that case also, in that case also M12 is equal to M21. Okay, don't don't worry about it. Okay, you can use this M12 is equal to M21 and calculate the induced EMF. Okay, I hope you have understood this. If not, you can ask me. You can stop me anytime. So is it clear to all of you? Is it clear, Pujita, Deepa? Deepa, is it clear? Sampad, is it clear to you? Mutual inductance and how did I calculate mutual inductance and all? If not, you can ask me exactly where you have not understood. Then I can again repeat it. Okay. Anyway, if you have understood, I am happy. All right. So then I'll just go to the next part. Next part is uh, our okay. One more point here. I just want to mention, if suppose some core material is there in this solenoid anywhere, here we have done in the air medium, so that's why M1 to M21 we got mu 0 N1 N2 then pi R1 square L, this one. So this is actually called free space permeability. Free space permeability. So if there is, so that means there is air in between. If you have some material, then you need to multiply the relative permeability of that material. So you have to just multiply relative permeability. This is called relative permeability. This is mu 0 N1 N2 pi R1 square L. So this is the change you have to do. Okay. Okay. Now we'll just go to the self inductance. As I said, self means the induction process by itself. I have a coil C1. If I have a current, AC current, suppose I have an AC current which is changing with time, varying with time. So what will happen, in this case, because a circular coil of current I will produce a magnetic field, okay, axial magnetic field. And see, when the current is changing, see, if the current is varying, magnetic field produced by it also will be time varying. And see, the magnetic field produced by itself will actually uh, will be, see, magnetic field lines will pass through this itself. So there will be a flux link in itself, okay, in itself. Suppose there are n turns in this coil, so n1 pi 1, this is directly proportional to the current in itself, okay, current in itself, if this is the thing, okay. So what I'm saying, if a time varying current is flowing in a coil, there is a magnetic field which is like magnetic field produced by this coil is also will be time varying. If the time varying magnetic field is varying, then there will be a flux which is linked also will be time varying, because the flux linked in this coil, in the same coil or in itself, is directly proportional to the current in itself. Okay, so if I just remove the proportionality, then I can write this as LIT. Okay, so there will be an induced EMF in this itself. This induced EMF will be minus ddt of n1 phi 1. So which is, see, this L is actually proportional to constant which is called self inductance. Okay, this L is called self inductance. Okay, self inductance. So I can write this is again proportional to this, so I can write this as minus L di dt. That means if a current is flowing in a coil and if that is time varying, then according to this formula there will be an induced EMF in the coil itself, and that induced EMF will flow or produce a current which will oppose the change in IT, change in the current. So because of the change in the current, the induced EMF is produced, and that induced EMF will produce a current. That means if it is anti-clockwise direction, okay, if it is anti-clockwise, the induced current will be actually clockwise direction, okay, clockwise. So this is I induced, suppose, and this is the original I. So induced EMF will flow a current opposite to the current in the coil, such that the change in the current will be not there or very less. So it is opposing the. So this is from like Lenz's law, okay. So since this current is opposite, so there will be there will be actually, you know, um, so this is called, since the current is opposite to the original current itself, so this is called back EMF. This is called back EMF. The self induction is called, see, due to self induction, a back EMF is created. What is the role of back EMF? To reduce the current in the circuit, reduce the change in the current, okay, reduce the change in the original current itself, okay. So that means, you know, a single isolated coil also can create or produce an induction, okay, produce an induced EMF due to the change in the current in itself, or due to the change in the flux in itself. So that's why it is called self induction. And since induced self due to self induction, the induced EMF will produce a current which will be opposing the original current itself. This is called back EMF. This is called back EMF. That means this back EMF is, if I say back EMF, you should have an impression that this is a bad guy. It opposes the change in the current, original current, or it reduces the current in the circuit, okay. So that is the back EMF. So if you look, if you want to, so suppose this current is actually maintained as a constant current, or current is still maintained, then you have to actually do certain work against this induced current, okay. So that we'll learn here. See, look here, that the work done will be doing against the back EMF to maintain the current in the circuit, or the maintain in the to maintain the current in the loop. You have to do certain work, and that work will be stored as magnetic energy. So that work will be stored as magnetic energy. We will be learning here. So in this case also, back, you see, for a single coil you can find out, see, the induced the self inductance, see, mu 0 ni, right, and n number of coils are there. So you can see mu 0 n square, area of the coil, and the I, and the length of the coil. So this is how you can, the similar way as I have done for mutual inductance, you can find out the self inductance as well. Here it is mu r, mu 0 n square. A is the area of the coil into L, okay. And see, as I said that uh, self-induced EMF is also called back EMF as it opposes the change in the current in the circuit. Physically, self-inductance actually act as an inertia in the electric circuit. So self-inductance plays a role as the mass in mechanics. Okay, we have learned the inertia in mechanics is mass of any object. So in electrical circuit, the inertia, you can look from here, the inertia is the self-inductance. Okay, so a self-inductance has the same role as the mass in mechanics. That means self-inductance gives the inertia because it is opposing the change in the current or opposing the current in the circuit. So that's why it is called inertia. Okay, inertia in electric circuit. So to remove or overcome that inertia, you have to do certain work, and that work done will be stored as magnetic potential energy in any current carrying circuit or loop where there is an inductor. Okay, there is when there is an inductor, there will be magnetic energy stored, and that energy is coming from the work done by the source itself. The source, electrical source, which is producing current in the or flowing a current in the circuit, that has to work against the against the back EMF to maintain the current in the circuit. So rate of change, if I write rate of change of current, look, sorry, rate of change of that work done, I'll just go to my presentation. So we are learning magnetic energy, magnetic potential energy in this case, in case of, so magnetic potential energy or magnetic energy. So self-inductance, see, self-inductance L, okay, self-inductance L, it is simply sometimes called inductance, simply inductance it is called. Whenever we say inductance, then it is meant uh, inductance meaning is actually self-induction only. If you say mutual, then mutual inductance M will come. All right. So if you have a coil in a circuit with the battery, suppose, okay, so it is flowing a current in this. You know, in the beginning, in the beginning, in the very beginning, what will happen? This inductor will oppose the current because of the back EMF produced in this. But if we want to maintain the current in this circuit I, then we have to do certain work, and the rate of work done is ddt of mod of this into I in the circuit. Okay. So what is this I? We know this is L di dt, and you have already I here. So I can write this like this. So now if you want to calculate the magnetic energy or the work done, total work done, then you have to integrate. Suppose this is 0 to W, and this is L goes off. Okay. So dt you can just remove from both sides, and you know this is L di, and suppose current is also increasing from 0 to I in the circuit. As soon as you uh, suppose this is not a DC, this is actually AC source. Okay, AC source battery. So this will give you W is equal to half L I square. This is called magnetic potential energy. Magnetic potential energy, okay, or magnetic energy stored in the coil. Okay, so you look here, we have magnetic potential energy, it is called EB, suppose half L I square, and also we know mechanical kinetic energy half M V square. If you just compare these two, see this guy and this guy, they are actually doing the same job. So in electrical circuit, L inductance is actually equivalent to the mechanical inertia, which is mass in the mechanical circuit. So that's why this is called, L is called electric inertia or electrical inertia in a circuit. Electrical inertia in the circuit, and this is obviously, simply inertia. Okay, and obviously I is actually equivalent to V. Okay, so this is what we can learn from. So this is the magnetic potential energy. You should remember how you should write magnetic potential energy for any inductor. So this is a stored energy in the inductor. Okay, so okay, now I'll just tell you one more thing, then I'll stop the class. The thing is, if you have simply a coil, if you have like two coils C1 and C2 nearby, actually you are having both the inductance, both L and M, both L and M. In that case, you should consider, see, when you are calculating induced EMF, you should consider both. Okay, D, okay, so sorry, L di dt minus M di dt. That means what? This is actually coming from mutual inductance, and this is coming from self inductance. Okay, or I can say self induction. The phenomena is called actually induction, and the constant, this L, is called inductance, self inductance, and this is called mutual inductance. So total induced EMF will be for both due to self inductance or induction, induction and mutual induction. So when you have been given two coils and calculate the induced EMF in the one due to the current in the other, you have to just remember that you have to take both mutual induction and self induction. Both the things you have to write. You look here in your book. Yeah, so this is what you have to write. So actually in general you can write this one, M11 minus M11 di dt, di1 dt. That means the current in the same coil, and this is current in the opposite coil, M12, the induced EMF in the coil 1 due to the current in the other coil. So this is called in mutual induction, this is self induction. Okay, so this is the one. So yeah, so this is the self. Okay, so M11 is actually called self inductance, which is written as L1 or L simply for a circuit. Okay, so yeah, so with this actually our discussion I'll just conclude, but if you have any doubt or any query or anything, you can just ask me now for 2 minutes, or otherwise I'll end the meeting. Deepa, Sampath, Sampath, you want to say something? You want to ask something? Deepa, do you have any problem to understand whatever we have discussed today?
No, sir. No doubt.
Okay, good. So then we'll stop. I think Sampath, his microphone is not on. I hope he doesn't want to speak. Sampath, if you have any question, query, you can just ask me, or otherwise, I'm just ending the meeting. You can message me, or if you have any query, you can send me through Guna madam also. Okay. Okay, then see you on Wednesday. Bye.
This conference will now be recorded.